Alright, folks, in this video, we're going to discuss VSEPR theory. VSEPR theory is an important theory that can help us identify the electronic geometry and molecular geometry of a molecule. Well, essentially in chemistry, structure and geometry, these are the two very important terms for us to understand the basic features of a molecule. Okay. So, and we have some procedures for us to follow to identify those geometries. Before we talk about VSEPR theory, let's take a look at the standard geometries. The first one is a linear geometry. Essentially, it means that if you have three members and all three members are on a straight line, then it's a linear geometry. Very easy to understand. Beryllium chloride here is a very good example. Okay, so you can see the angle between the two bonds is 180 degree. Next one is a trigonal planar geometry, and essentially you have four members. All four members, all of them are in the same plane, and the angle between the two bonds, all of them are 120 degree, and then we call it trigonal planar geometry. Tetrahedral geometry, and you would have five members, and the angle between two bonds is 109.5. That's the standard tetrahedral geometry. Okay, so for tetrahedral geometry, as you notice, unlike the linear geometry and the trigonal planar geometry, in which the three members or four members, they are in the same plane, this one here, the five members, they are not in the same plane anymore, right? And you can see that this one is a little bit if this screen is a paper, this hydrogen is behind the screen and this hydrogen is above the screen, okay, or paper. If you treat these three as in the same plane, we know that the 3 points define a plane, right? All right, now how do we draw the three-dimensional geometry of tetrahedral on the paper? Well, here, like I said, that if you want to draw it, then the carbon and the hydrogen, these three atoms, they are gonna be in this screen. Okay, these three are in the same plane. Or for this hydrogen, since it's below the screen, then we use dashed wedge to present the position of the hydrogen behind the screen or below the screen. And we use a solid wedge to indicate that this hydrogen is above the screen. Okay, and this is how we use a dashed wedge and a solid wedge to indicate whether an atom is behind or above the screen or the paper plane. Okay, all right. This is tetrahedral geometry, and the next one is trigonal bipyramidal geometry. And you can see that it has total 6 members. And again, like tetrahedral geometry, some of them will be behind the screen, some of them will be above the screen. And we will use the wedges to indicate the positions of those atoms again. Okay. Before we do that, I want to remind you the bond angles. Well, you can see that there are 3 types of bond angles in this molecule, in this geometry. The first one is the 90 degree. So this chlorine, phosphorus, and this chlorine, the angle is 90 degree. This chlorine is perpendicular to this PCl bond. And if you check the other 2 PCl bonds, okay, you can see that this chlorine is also perpendicular to this PCl bond, also this PCl bond. Okay, so you have 90 degree also here for these two. Same thing here for this chlorine. It is also perpendicular to this bond, this PCl bond, this PCl bond, and this PCl bond. Again, so you would have 90 degree for this bond angle, this bond angle, and that bond angle. Okay, so this is a 90 degree. How about 120? If you are talking about those 3 chlorines and this phosphorus center. These four atoms are in the same plane, like the BF3, okay, trigonal planar geometry. And we said that this triangle plane is called the equatorial plane, okay. And if you take a look at the bond angle of CLP and this PCl bond, that is going to be 120 degree, okay. So this, and also this bond angle and this bond angle, okay. So that is 120. The last one here is 180. If you are talking about this bond and this bond, as you notice, they are on the opposite direction. So therefore, for these two bonds, it's 180 degree. Okay. Now, how do we use wedges to indicate or to draw the three-dimensional structure of trigonal bipyramidal geometry? I'll write it here. Okay. So you have P, Cl, NCl, and Cl. These four members, they are going to be in the same plane. Okay. These four. Okay. And this chlorine is going to be behind the screen, and this chlorine is going to be above the screen. So again, we use dashed wedge and solid wedge to indicate the positions of those two chlorine. That is how we draw trigonal bipyramidal geometry. The last one here is the octahedral geometry. Okay, and you can see that it has 7 members. And again, bond angle, this fluorine is perpendicular, or this fluorine sulfur bond is perpendicular to the other 4 SF bonds, so 90 degree. And this fluorine sulfur bond is also perpendicular to the other 4 SF bonds, so 90 degree. And on the equatorial plane here, you can see that these 5 members, okay, they are in the same plane, and so the bond angle here is 90 degree also, okay, 90 degree. Now the second type of bond angle is these two bonds, this sulfur fluorine bond, this sulfur fluorine bond. They are on the opposite direction, so the bond angle is 180. Okay. Now how do we draw the three-dimensional geometry of octahedral on a piece of paper? Well, here is this. So you have sulfur, fluorine, fluorine. These 3 atoms, they are inside this screen, and then this fluorine, okay, this one here would be below the screen, so we use dashed wedge. And same thing for this fluorine, it's below the screen. And how about the other 2? They are going to be above the screen, so we use solid wedge. Okay, so these fluorine are these 2. So this is how we draw the three-dimensional geometry of octahedral in the two-dimensional plane. All right, now these are the standard geometries. Now, how do we figure out the geometry of a molecule based on VSEPR theory? We have 4 steps for you to follow. The first one is you need to draw the loose structure. Okay, so this is the second video of chapter 5, how we draw loose structures. That you have to be careful when you draw loose structures. Okay, if you got the loose structure wrong, then the following procedures, they are going to give you the wrong results. Okay, so first step, loose structure has to be correct. Second, determine the total number of electron groups around central atom. Okay, so the electron group here means 2 things. All right, I'm going to write it here. That means either bonds or lone pairs. Okay, both bond and lone pair, they are called electron groups. Okay, and you just need to count how many of them you have on the central atom here. Now the third one, determine the number of the bonding groups and number of the lone pairs. So you treat them separately in step 3, and then according to the number you have here from step 3, you determine the electron group, electron geometry, and molecular geometry. Okay, we'll do examples in a moment. Here, this website, I highly recommend you go to this website and check out these animations. Okay, it's amazing. You should do that, because in this on this website you can create the geometries by adding bonds, or even sometimes double bond or triple bond, and visualize the three-dimensional geometry of those molecules, because you can drag and you can rotate the electron, and you can take a look at the bond angle. It's very useful, and it gives you, this website also gives you a bunch of examples about the electronic and molecular geometries. Okay, so you can use that as a practice purpose. All right, so these are the procedures, and this is a table that can help us identify the molecular geometry and electronic geometry. And here it lists the bond angle also, and you can see that it has 3-digit codes. Okay, our job is to identify the 3-digit codes. The first digit here is electron groups from step 2, bonding groups from step 3, lone pairs from step 3. Okay, so once you identify the 3-digit code, then you should be able to identify both electron geometry and molecular geometry. These are the examples for you to try. Okay, in the following slides, I'm going to show you a couple of examples. And another thing that I want to mention here is this table will be given in your test. You don't need to memorize anything. You just need to know how we use VSEPR theory to identify the geometries. All right, let's do some examples. Okay. The first one is the carbon dioxide. Okay, as the first step says that you need to draw the loose structure of carbon dioxide. All right, let's draw that. It's going to be CO double bond and CO double bond. Okay, now first step is done. The second step, determine the total number of electron groups around the central atom. Well, you can see that for central atom carbon, it has 2 bonding groups, no lone pair electrons, right? So the total number of electron groups would be 2. All right, would be 2 right here. And number 3, step 3, number of the bonding groups, number of the lone pairs. Actually, we just did that when we talk about the number 2. So number of the bonding groups 2, and 2. Number of the lone pairs would be 0. So it's going to be 2, 2, 0. So 2, 2, 0 right here, it tells you electron geometry would be linear and molecular geometry would also be linear. Okay, so this is how we identify the both geometries for carbon dioxide. Okay, next example is CHCl3. Again, first step, draw the loose structure. It's going to be CH, Cl, Cl, and Cl. Okay, now step 2, determine the total number of electron groups. Well, for central carbon atom, well, you have 1, 2, 3, 4 bonds, no lone pairs. Okay, so total number of electron groups would be 4. Number of the bonding groups 4, and the number of the lone pairs would be 0. So the code is 4, 4, 0. So 4, 4, 0. You can see that it's right here. Electron geometry tetrahedral, molecular geometry tetrahedral. All right. And then how do we draw the 3-dimensional geometry of the CHCl3? Well, here is the time for us to use those widgets. Okay, you can put any 3 atoms, okay, on this screen plan. Of course, one of them has to be the central carbon. Okay, then put the other two atoms accordingly. Well, one of the chlorine apparently would be behind the screen, and one of them should be above the screen, like we did for the standard tetrahedral geometry. Okay, this is how we show the three-dimensional geometry, three-dimensional molecular geometry of chloroform. Okay, CHCl3. Okay, so this is this example. Next one, NH3. Well, if you draw the Lewis structure of this molecule, it will be something like that. Well, lone pair, hydrogen, hydrogen, hydrogen. Okay, now be careful. Determine the total number of electron groups. You have one lone pair, 3 NH single bonds. Therefore, total number of electron groups would be 4. Now, determine the number of the bonding groups. We know that bonding groups, it has 3 bonds. All right. Therefore, the bonding groups would be 3. And the number of lone pair, apparently, it's just one lone pair. So the last digit of the 3-digit code is 1. 431. Let's take a look at this table. 431 is right here. Electron geometry tetrahedral. So when you consider both bonds and lone pair, it's going to be tetrahedral. However, if you are talking about the molecular geometry, it's going to be trigonal pyramidal geometry. In other words, when you consider molecular geometry, you consider those atoms only, okay, or bonds only. You ignore the presence of lone pairs when you consider molecular geometry. Now it's time for us to draw trigonal pyramidal geometry. Well, here is what you can do. Like we did for standard tetrahedral geometry, you put the lone pair and one of the NH bonds in the same plane, in this screen, and then one of the hydrogen would be behind the screen and the other hydrogen would be above the screen. Okay, so this is how we identify the geometry. Now, I want to remind you about the angle, bounding angle. For a standard tetrahedral geometry, we know it's a, let me show you, it's a 109.5 degree. But here, this bound angle is not going to be 109.5 degree anymore. Why? It's because this lone pair, it occupies a little bit more space than a single bond. Therefore, this lone pair is going to push those 3 hydrogens towards each other a little bit more than standard tetrahedral. Therefore, this bond angle should be a little bit less than 109.5 degree. Okay, if you pay attention to what we have here, is it's less than 109.5. That's what it means. Okay, all right. Next example, SF4. If you draw the Lewis structure, it will be something like this. Lone pair on sulfur, 4 fluorine atoms around sulfur. Okay, so this is a Lewis structure. Now let's identify the number of the total number of electron groups. You have 1 lone pair, 4 bonds. Therefore, first digit 5. Second digit number of the bonding groups. You have 4 single bonds, 4, and 1 lone pair. It's going to be 1. 5, 4, 1. Let's take a look. 5, 4, 1 is right here. Electron geometry, trigonal, bipyramidal geometry. Molecular geometry would be the sensor geometry. This is how the sensor geometry looks like. In other words, let me draw the standard tetrahedral geometry for you. Okay, so this is the central atom here. Okay. Okay. Standard trigonal bipyramidal geometry. Okay. Well, you can see that this 4 atoms, they are in the same plane. But how about that one of the electron groups in this trigonal bipyramidal geometry is a lone pair? Which position we should be replaced by the lone pair? Well, you have two options, right? The first option, let me draw the two options for SF4. The first option is you have lone pair occupy. Let me draw the lone pair on the other side so you can match with the standard trigonal bipyramidal geometry. Lone pair will occupy one of the three positions on the equatorial plane. All right. The other option is sulfur. The lone pair occupy one of the two positions on the axial positions. Which one is correct? Okay, you have two options here and here. Which one is better? Well, the thing is, remember, lone pair is a little bit larger than a single bond because it occupies a little bit more space. The reason, lone pair belongs to sulfur. This two electrons is shared by the sulfur and fluorine. Therefore, those two electrons are closer to sulfur. They occupy a little bit more space on the central atom. Okay, so because of this, those four atoms, surrounding atoms, they want to stay away from this lone pair as much as they can. If you have lone pair occupy one of the two positions on the axial positions, then you have 90 degree, 90 degree, 90 degree with three fluorines, okay? And of course, 180 degree with one fluorine. Here, this lone pair, you have two 90 degree, two 90 degree, and then you have two 120, right? Now, because those four fluorines, they want to stay away from this lone pair as much as they can, the less 90 degree you have, the better the structure, okay? That means that this is the right structure for scissor geometry, and this is not correct. All right? All right. Now, next example, before we move on, I want to mention bond angle. The bond angle, as we mentioned, that for a standard trigonal bipyramidal geometry, you have 180, 90, and 120. Remember? However, for this scissor geometry, it's not a standard. And when you consider the electron geometry, it says that this is a trigonal bipyramidal geometry. But if you are considering the molecular geometry, because these two, this lone pair will push this two fluorine towards this direction a little bit, so this bond angle is not 180 anymore. It's less than 180. Okay, and this angle, so SF bonds and this SF bonds, they are not 90 degree anymore. They are going to be less than 90. Can you see that right here? Less than 90 and less than 120. Less than 120 means these two fluorine will be closer to each other a little bit. So these two bonds form an angle that is less than 120. Okay. When you talk about these two bonds, okay, and this one is going to be less than 90 degree. Okay. All right. Let's move on to next example. I3 minus. Well, again, let me draw the loose structure of this compound. It's going to be something look like this. You have three lone pairs on iodide. Okay, of course, a bracket, a negative sign outside the bracket. Now, let's get the code. Well, the first digit total number of electron groups, you have 3 lone pairs, 2 bonding groups, therefore first digit 5. Now 3 lone pairs, 2 bonding groups, so that's second digit bonding groups, that's going to be 2. 3 lone pairs, last digits 3. So 5, 2, 3, where it is? Well, right here, 5, 2, 3. Trigonal bipyramidal geometry for electron geometry, linear geometry for molecular geometry. In other words, these 3 atoms, they are going to be on the same straight line, and you have those 3 lone pairs occupy the equatorial plane positions of the trigonal bipyramidal geometry. Then how do we use wedges to indicate the positions of the lone pair? Well, here is what you can do. Iodide, iodide, and iodide. These 3 atoms are on the axial positions, and for the 3 lone pairs, you can draw a line. Okay, remember this is not a chemical bond. It indicates that the positions of this lone pair. Okay. Now for the other 2 lone pairs, one of them should be below the screen, so you use dashed wedge. Okay. All right. For the third pair, you use solid wedge and the 2 dots. Okay. So you can still use wedges to represent the positions of those lone pairs. There's no doubt about that. Now for bond angle, this apparently would be 180 degree. Okay, and we don't need to discuss the angles among the lone pairs, so you don't need to worry about that. There is only one bond angle for those 3 for those 2 I bonds. Okay, so it's just going to be 180 degree. Okay, now the last one in this video is going to be SBF6 minus. This is an Ni again. Now the loose structure is going to be antimony in the center, and fluorine, 6 fluorine of surrounding atoms. Okay, so this is a loose structure of this molecule. All right, now how do we get the geometries? Well, let's find the code. Total number of the electron groups would be 6. You have 6 bonds, and the bonding groups apparently would be 6, and no lone pairs on antimony, so it's going to be 0 for the last digit. So 660, it's right here. Okay, octahedral geometries for both electron geometry and molecular geometry. Okay, so this one is a little bit easier. Because there's no lone pair on the central atom. How do we draw the 3-dimensional geometry? By using wedges, like we did for the standard octahedral geometry. The wedges, solid wedge and dashed wedge. Okay, fluorine and fluorine here. Okay, and this is how we indicate, how we draw the 3-dimensional geometries of this Ni. All right. We'll come back to class and do more practice. And you let me know if you have any questions.